Okay, so I'm going to get started. Today's announcements are the same as they were last time. Just the exam review is going to be Sunday 2 to 4 p.m. in Math 100. And the exam is going to be Tuesday 7 to 9 p.m. in Chem 140. So it's looking like I will be able to finish all the reactions from Chapter 19 today. But I probably won't get to the synthesis practice, so I'll just do that on Monday. So everything from Chapter 19 will probably be fair game. And I may reassess or reconfirm that at the end of today's lecture just to be sure. Okay, questions about that? All right, cool. So we got a few more reactions of carbonyls to get through in this chapter. The first one that we're going to look at is reactions with amines. Okay, so I guess when I put up the roadmap at the start of this chapter, I sort of showed two different products that have nitrogen in them, and they look fairly similar, or at least one of them looks fairly similar to a carbonyl, and then one of them looks kind of different. So what we're looking at in this section is a mechanism that's actually kind of similar to acetal formation. So we're doing a ketone or an aldehyde plus an amine. Basically, it starts out like acetal formation mechanisms. Okay, so I won't draw the acetal mechanism up again, but I'll do this new one, which is about the same thing. Okay, so if we have our ketone here, and we protonate it, I guess I should say specifically like the acid-catalyzed acetal mechanism, because usually you're going to do this in a very small amount of acid. We can talk about the details on that in a second. Okay, so we get our protonated carbonyl. It's more electrophilic. And then just like we did with an alcohol, we can have some amine of our choice. And I'm just going to call it a secondary amine, like something with two R groups on there for the time being. You can have that come in just like ROH would have done in the last set of reactions we looked at. And that gets us to here. And then we can have something come in, deprotonate the nitrogen. And get us to here. Okay, so this is pretty much the equivalent of when we made a hemiacetal. And we can start, because we're an acid, we can start going towards what looks like kind of like a full acetal. So if you remember, because we're an acid, we can protonate this OH one more time, turn it into a good leaving group. And then have it drop off just like an alcohol would have done back in OChem 1. But again, just like when we're doing an acetal, the lone pairs on the other atom here can kick in and stop a carbocation from ever having to exist. So we end up with, and I'm actually going to flip this upside down from how it is in the notes, just to make it a little bit easier to follow. Okay, so that gets us to here. All right, so if we're doing everything pretty much exactly analogous to how we did it with acetal formation, at this point another molecule of nitrogen would come in, attack here, and it would end up with a carbon with two different nitrogens coming off. I think for reasons related to bond energy and like heats of formation, that actually turns out not to be the most stable outcome for this reaction. So something else is going to actually happen from this point on. And exactly what that is actually kind of depends on what's going on at the nitrogen here. Okay, so this form, I don't think I explicitly say this in the notes, but this is called an iminium. The IUM, like a lot of other things we've seen, just means something with a positive charge. But we actually have two different options on how to wrap this one up. One is if the nitrogen really actually has one alkyl group and one H. So in other words, if one of the R groups that I've been showing on there this whole time was really an H all along. So in other words, if the nitrogen really had just one alkyl group to start out with and actually had a couple H's. In other words, our starting material would have been a primary amine. Then, the easiest way to finish this reaction up, we've got a positive charge on the nitrogen. If one of these is an H, let's just pull that H off, get rid of the positive charge, and we're done. So in that case, it's just going to look like this. And now it's kind of like we've seen a few mechanisms where the last step involves just pulling a proton off of a carbonyl and getting back to like a neutral double bonded atom. And in this case, because it's a nitrogen, it needs to have an extra group coming off of it in order to be neutral with a phyloctet. Okay, so this is kind of upside down from how I have it in the notes, but it's the same thing. Carbon double bonded to a nitrogen with one R group coming off of it. This is called an imine. Okay, so that's kind of the easy way out of getting rid of this plus charge and finishing up the mechanism. What if we don't have that option? What if we can't deprotonate the nitrogen, the iminium? So if the N actually does have two alkyl groups, two actual R groups, so in other words, the starting material was a secondary amine, then we don't have the ability to pull an H off the nitrogen, but we do have the ability to pull an H off of a beta carbon. So it's kind of like we're doing an E2. It's not exactly an E2 because we're not kicking out an entire leaving group. What we are kicking out is the pi bond to the nitrogen. Okay, so how that looks. Okay, so we're here at the iminium. This time we're looking at we can't actually quench the positive charge on nitrogen directly by pulling either of these R groups off because they're not a proton. They're not going to come off even remotely easily on their own. But if we have H's on a carbon that's one away, we can actually do something where whatever base we have comes in, takes the H, and then this does kind of an E2-like step where you're getting rid of an H, a proton from one carbon, and you're getting rid of the pi bond to the nitrogen from the other carbon. So that's kind of your leaving group such as it is. And that is going to get us a carbon-carbon double bond, just like real E2 did. So we're making a pi bond between carbons here. And now we're getting this thing forming instead. So this is the enamine group that I showed at the start of the chapter. It's an alkene attached to an amine, kind of like an enol, only this thing doesn't actually have any motivation to tautomerize the way that an enol would. Okay. So pretty much the only difference between the last step of the mechanism between these two different options is, do you have an H you can pull off the nitrogen easily or not? Okay, so questions about that? Yeah? So I guess like you could show a resonance form where like this kicks down and this kicks onto a minus charge on the carbon, but that's going to be real minor just because here everything's neutral and like putting a negative charge on carbon is to be avoided if you possibly can. Yep, but at least everything would have a full octet, so that's something. Okay. Other questions about this mechanism? Okay, so overall reaction. Oh, you know what? Actually, one other thing I should add to this. Primary amine is one way to do this. The other option is if nitrogen has two H's, you can still do this. So starting material is primary amine, or it could have no R groups and you could still do this mechanism. And then instead of R and H, it would just be H and H, and then you still do this part just fine. Okay, so overall reaction. We're going to show three different ones depending on how many R groups there are on the nitrogen to start out with. Here's a ketone, NH3 and H+. Gives you this imine here with just an H on it. Or you can do it with a primary amine, R, NH2, and H+. And it still gives you an imine, only now it's got an R group on there. Or if you try doing this with a secondary amine, an H+, this is where we start running into the enamine, because it's pretty much the only way out to finish the mechanism. Okay, what would happen if I tried doing this with a tertiary amine? Like how far through the mechanism would I get before I got stuck? I guess that's sort of an open-ended question that you guys might not be able to answer as a group, but let me scoot this back down here. This is not really amenable to short answers being shouted from the audience, but so if I tried this with a tertiary amine, then I would have 3 R groups on here. This step might work okay, like the lone pair could still attack, but then as soon as I get to this point, that's it. I can't do that. I can't deprotonate. And then like I just sort of slide back down the reaction curve and go back to starting material. Like there's no way to get it to stop at any reasonable product at that point. Okay. All right, so questions about that one? Okay, cool. So one quick side note on this. I'm leaving it real vague about catalyst here. Turns out this one is actually kind of finicky about the exact amount of acid that you use, because if you throw in a ton of acid, all that's going to happen is you stick a proton onto the nitrogen, which is also protonatable, it's also basic, and then it doesn't have a lone pair free to go do the attack. So this one you usually actually will set up at a pH of about 5-ish is kind of traditional for this reaction. I'm going to leave it vague enough that you can just write H+ on the arrow, but in reality, like this one, you actually have to fine-tune things a little bit more than I'm getting into. So, okay. All right, so that's amines, imines, and enamines. Turns out there's some other useful stuff that you can do with these, but there's a whole chapter devoted to nitrogen later on that we're going to cover, like things you can go to from here. For the time being, this is just like if you start with the aldehyde or ketone, here's what you can do. Okay, so a couple more categories before we're done with this chapter. Okay, so we covered a whole group of reduction mechanisms. And we covered what happens if you turn your 2 bonds to oxygen into 1 bond to oxygen if you go down to the alcohol. But I also mentioned at the start of the chapter, you can go all the way down to 0 bonds to oxygen if you set this up right. So reduction to alkanes is kind of what we're going to look at here. Okay, so there's actually 2 totally different reactions here, and sometimes you want to use one, sometimes you want to use the other. We'll cover both of them, and then like how to pick when to use one or the other. Okay, so we're not actually going to get into the mechanism for either of them though. One of them because it's kind of transition metal based, and the other one because, to be honest, it's not that useful to know. So Wolff-Kishner, you start with a carbonyl, and the reagents that you're going to use are H2N, NH2. This one is actually hydrazine. And if you look at it, it's 2 NH2 groups stuck together with a single bond. Kind of a side note, this one is actually fairly commonly used as rocket fuel. Because pretty much any excuse you can give 2 nitrogens to form a triple bond to each other and go off as nitrogen gas is going to be a very, very strong driving force for the reaction. And that turns out to actually be what's happening during this reaction, although we don't get into the mechanism for it. That's also happening in rockets as well and liberating a ton of energy. So you might see it written as H2N, NH2, or you might see it written as N2, dang it, N2H4, any of those all mean the same thing. And then you also need base, heat, and sometimes they'll list a solvent that's really high boiling, like triethylene glycol is real common. But to be honest, the solvent, the exact details don't really matter. It's just like doing this in reaction. You have to actually heat it up to maybe like a couple hundred degrees, and you want a solvent that's not going to boil off under those circumstances. Or you can do this in like some pressurized vessel, and hopefully the rocket fuel doesn't get any ideas about that. Okay, so we're not getting into the details of exactly what's going on here. It actually, okay, so maybe a little bit of the details in case you're curious, but the mechanism for this actually starts out looking a lot like imine formation, where you take one of the nitrogens here, which is sort of like a primary amine, and you start out making the imine out of it, and then things sort of go off on a tangent, and you end up at the end kicking out N triple bond N. If you're curious, I think the solutions manual works through that, or you can sort of puzzle it out yourself, but anyway, long story short, that's kind of where we're going with this. Okay, so one thing that is worth pointing out is that you need fairly strong base to do this, and so don't use this if you have other functional groups on your molecule that are sensitive to base. We haven't seen too many base-sensitive groups so far. That's not true. We've seen alkyl halides. Like if you had an alkyl halide somewhere else on the molecule, this would not be a good choice because the KOH is a strong base, good nucleophile. That would go mess your stuff up at the alkyl halide, and then you might be doing inadvertently some reaction elsewhere on the molecule as well. Okay, so be careful about that. The other one is called Clemenson Reduction. And this one is one that uses transition metals. So for this, we're actually going to use something that's written as ZnHg. So this is zinc and mercury mixed together. This is also called zinc-mercury amalgam. Or because a lot of amalgams, like, is kind of an old term for two metals mixed together. But traditionally that was done with mercury with whatever other metal. So this might also just be written as zinc amalgam. And then you also use HCl and ETOH. Okay, so again, we're not going to get too much into the mechanism for this. I think it involves like some fundamental transition metal steps that we're not going to look at. But it does the same thing overall. Replaces 2 bonds to oxygen with 2 bonds to H. But sort of the kicker here is that this one uses acid, HCl. So if there's anything in your molecule that's sensitive to acid, this would be one to avoid unless you want that other thing to get messed up. So here, base means avoid any kind of alkyl halides. So avoid if you have alkyl halides in the molecule, base is a bad idea. HCl, we know reacts with a bunch of things. Alkenes are probably the most careful thing, or the most vulnerable to acidic conditions that you need to be aware of. So avoid if you have alkenes. There's some functional groups that are going to be pretty screwed under both of these conditions. So like if you had an epoxide in your molecule, we know those react with acid and base, and so neither of these reactions are going to be a good choice then. And so then you have to figure out some other like entirely different synthetic route. But between the two of these, you have sort of a good pair of, you know, maybe your molecule is sensitive to one but not the other, so you can probably figure out a way to get it to work. Okay. So the reason, I guess like not the only reason, but a very useful application for these actually ties back into chemistry from a couple chapters ago. Because these are very useful if you combine them with Friedel-Crafts acylation. Okay, so I kind of mentioned a few chapters ago that there's some alkyl groups that you just straight up can't do by Friedel-Crafts alkylation because we know the alkyl group is prone to carbocation rearrangements. So if we were trying to do like, say, butylbenzene, we might think, okay, let's just use butyl chloride and AlCl3 and stick on a butyl group. But that's not going to happen because even though we're going for, you know, you pull off the chlorine, you make a carbocation, it makes this. The alkyl halide has other ideas. And it's going to rearrange to make sec-butyl benzene instead. Okay, so what these reactions, Wolff-Kishner and Clemenson allow us to do is use acylation to stick on the group that we want, so long as it's primary at the point of attachment, and then lop the carbonyl off afterwards once we're done using it to anchor our carbocation or our positive charge in place. So what we're going to do instead is we're going to do a Friedel-Crafts acylation, get a carbonyl on there. Get our acyl group on there, and now we don't have to worry about rearrangements. And now we can use one of these new reactions to get that carbonyl off of there and get the alkyl group that we want. So should I use Wolff-Kishner or Clemenson or either in this reaction? Either, yeah. Or either, yeah. Yeah, because there's nothing else in this molecule that's going to get messed up by either of those conditions. Either acid or base is totally fine here. So either Wolff-Kishner or Clemenson in this case would be totally A-okay. If I had stuck on like a longer chain that had some other bits hanging off of it, maybe like an alkene somewhere along its length or something, then I would be a little bit pickier about which particular one I chose out of those two. But here it totally doesn't matter. Okay, so questions about that one? Okay, cool. All right, so last reaction from this chapter, actually. How are we on time? Okay, nice. Okay, so I know it's spelled with a W, but this guy was German, so it's pronounced Wittig with a V. If I hear you say Wittig, I will probably wince a little bit. Okay. So this one is the Levitic Synthesis. Okay, this is another very useful way of creating carbon-carbon bonds, and it's actually extremely flexible and useful because it actually makes a brand new alkene in our molecule, and we have a lot of choice over what all is attached to either side of that alkene. So this is the one, I guess when I put up that roadmap of carbon-carbon bond forming stuff at the start of the chapter, this is the one that's sort of conceptually the reverse of ozonolysis. It uses totally different reagents, and it's not at all the same mechanism or anything, but at least conceptually, like in terms of what you're doing to the molecule, you can sort of think of it as like the opposite of ozonolysis in some ways. Okay, so here's how we're going to set it up overall. So we start with our aldehyde or ketone, and we're going to bring in another reagent, and I'll explain more about this in a second. But if you guys remember triphenylphosphine that we saw in the transition metals chapter, a phosphorus with 3 different phenyl groups off of it, it's going to be that, but phosphorus can violate the octet rule, so it's actually going to be shown a lot of the time, although not always, as we'll see, as phosphorus with a double bond also onto a carbon that has pretty much any 2 R groups of our choice coming off of it. Okay, so we'll cover how to make this one in a second too, because sometimes you have to make your own for the synthesis. So this is called a Wittig reagent, and there's a couple other descriptors that we'll talk about because there's some interesting things going on there. But basically, I guess you could also think of this as somewhat analogous to alkene metathesis as well, because what we're going to do is slice right across both double bonds and sort of switch around what all is double bonded to what. Unlike alkene metathesis, we don't have a ton of options. We only have one possible pairing that's driven by the fact that, as it turns out, so this isn't even our major product, it's a byproduct of what we're getting. But as it turns out, phosphorus and oxygen really like being double bonded together. And so they're just going to go off together, and then the other two groups are sort of left to form a double bond, which happens to be exactly the product that we care about. So we're going to get this thing double bonded onto the other half of what used to be the Wittig reagent. So like that. Okay, so this is, I think, triphenyl phosphine oxide, I think. And this is actually, like, the fact that this can be created is what's actually pulling the thermodynamics of the reaction in our favor. And the alkene, like, thermodynamically is just sort of an afterthought, even though that happens to be the entire reason we set this up in the first place. Okay, so that's kind of the big picture. Questions about that before I get into how that works? Oh, yeah?
Is the alkene the major product, or is that like...
Mm-hmm. Yeah, so this is just a byproduct. You wouldn't even bother drawing this most of the time. So this is the part that we actually care about. I just think it's funny that, like, thermodynamically that doesn't even matter, and, like, this is the whole reason this reaction is favorable. So, okay. So some more details about the Wittig reagent and how it's made. And I'm going to turn it sideways here just because it's a little bit easier to show it getting formed this way. Okay, so pH3P double bond to carbon with whatever R group's on it. Okay, so we can show it in the double bond form there, but it has another major resonance form that turns out to be this thing, weirdly enough. I'm actually not sure about the relative electronegativities of carbon and phosphorus. I guess carbon has to be slightly more electronegative if this is happening, but it may also be driven by, if we go to this resonance form, then phosphorus actually is not violating the octet rule anymore. But yeah, this is actually, I think, roughly equal as a contributor to the resonance forms as this thing is. Okay, so you can show it in either one of these. Like, I could have drawn this charged version during the reaction up there, and that would also be totally fine. So this reagent is got a couple of terms attached to it. One of them is Ylide, so that's spelled Y-L-I-D-E. And it's also called zwitterion. And so, yeah, so you might hear either of those terms thrown around, Ylide or zwitterion, or zwitterion, I guess, if you're pronouncing things properly. A lot of German chemistry involved here. But these pretty much mean the same thing, and that is something with a positive and negative charge, usually on adjacent atoms. Okay, I think the term Ylide means they have to be on adjacent atoms, and zwitterion means they can be anywhere on the molecule. But for Wittig, it's kind of a moot point because they're always going to be on adjacent atoms. Okay, so the fact that we can draw it with these charges actually gives us some hint as to how we're going to make this in the first place. So whether you actually have to make your own Wittig reagent here is kind of depending on the exact constraints of the synthesis problem that you're given. So if I say, like, I want you to make this alkene and start with this carbonyl, or, you know, whatever, and I don't give you any other constraints at all, you can just show up with this whole thing all ready to go and purchased from whatever chemical company, and you don't have to make your own. But if I say, like, make this alkene from this carbonyl and then something with a limit of, you know, this many carbons, then maybe this is too big to actually have you show up and start it in synthesis right away. And then you would have to show how you made this thing yourself. So let's look at how to do that if you need to. Okay, so how to make your Wittig reagent. You're going to start with phosphorus with 3 phenyl groups on it, which you'll note is actually one of the ligands we saw a whole bunch of in chapter 18. Like triphenylphosphine shows up a bunch of places. It's kind of useful not just for transition metal chemistry, but for doing this stuff as well. But here we're not using it as a ligand. We're actually using it as, okay, so we've got, actually I'll show it like this. Okay. So we're going to bring in an alkyl halide that has the 2 R groups on it that we want. And it also has an H and a leaving group. The first step is actually just going to be straight up SN2. So whatever's going on here with your R groups, it has to be something that permits SN2. So if that doesn't work, you're going to have a hard time. And this is not going to work if that doesn't happen. Okay, but assuming that we're good on that point, now we have this going on. The carbon ended up neutral because it had electrons coming in and going out. But the phosphorus, when it did this attack, it lost some charge density from its lone pair, and so it's now positive charged after this step. So technically, I guess we also have like the leaving group hanging around nearby to cancel that out. Okay, so we're actually pretty close to this ylid thing already. We just need to do one other thing, and that is remove a proton here. So for this step, we need a very strong base, and usually butyl lithium is like the traditional choice here. There's other choices as well, but that's kind of a good default to use. So butyl lithium we bring in, that rips off the H. We get the negative charge on the carbon. And that gives us our ylid form, which we can show in resonance to the double bonded form if we want. Okay, so overall, ylid formation is going to look like whatever alkyl halide we have. We say first step 1 is triphenylphosphine, and then step 2 is butyl lithium in the same solvent we always use for organometallics, either THF or ether. And then that gets us our ylid. And then from there, we can plug that into whatever carbonyl we want it to react with and make a, like whatever our desired alkene is out of that. Okay, so questions about that part? Yeah?
Did you say that ylid resonance form was just as dominant as the other one?
So I know they're both like pretty major contributors. I don't know which one is slightly more favored than the other.
I was wondering why, because there's the octet on the carbon.
Yeah, so I guess like the difference between them is like this one phosphorus violates the octet rule, and this one it doesn't, and I don't know like how big a driving factor that is for one side or the other. Yeah. Okay. So other questions about this? Yeah.
When we draw the reaction mechanism for this, can we use like the
The fine notation? Yeah, that's totally fine. Like I tend to do pH just because I can type it easier that way in the notes. But yeah, like whatever works for you, like handwriting wise, or you can actually draw out the phenols if you want. They're all the same thing. So yeah. Okay. Sorry. Yeah. That, or I might go further back and like have you like have to make your own aldehyde or ketone at some point along the way. So yeah, I guess there's a bunch of ways I could set that up. Let's see how much time I got. Okay. So I might skip it for now in the interest of getting the last reaction done for the day, and then like I was thinking on Monday, because I'm probably going to get through this example synthesis practice thing in the notes, probably like the first 20 minutes or so on class on Monday. And then I might just spend the rest of the time on Monday just doing like synthesis practice with you guys and not introduce new material until like after the exam, if that works. So I guess that's also like if anyone can't make it to the exam review thing on Sunday, then this at least gives you like some exposure to like synthesis practice. I mean, hopefully you've done practice problems on your own, but like seeing it all together might be helpful. So. Okay. Okay, so any other questions about this one before I sort of move on to what is actually the very last reaction in this chapter? I thought it was Wittig, but I forgot there's this last one. Yeah? Yep, yeah, sorry, the chalk is kind of garbage, but yeah. Okay. So last reaction in the 8 minutes or so that I have left. And I guess this one is really kind of a review of one from OChem 1. But we're looking at it in a different light now. And that is oxidation to acids. So we already know that if you take a primary alcohol and you do some sort of strong oxidizer, let's just write it as Jones, for example. At first what it does, I'm going to put square brackets around this because it doesn't stay here very long. So primary first, and then aldehyde is what it passes through very briefly on its way to the carboxylic acid. So we've seen that in the past. But you can also totally just take an aldehyde and start like halfway through the oxidation sequence and also just go to an acid. So if you're starting with an aldehyde, you can just go straight to the carboxylic acid, again using Jones or whatever reagent you want of the strong oxidizers. Okay, so I'm not going to write up all the different combinations of reagents we could use for this, but it could be written as Jones, or it could be written as basically any form of chromium or magnesium or manganese with a bunch of oxygens attached to it, so long as it's in a protic environment and it's not like PCC and DCM.
Is the aldehyde just considered the transition state of that?
More of a reaction intermediate, I guess, but yeah. Mm-hmm. Yeah, so it's basically like if you're hitting this thing with Jones, like it's going to briefly exist as the aldehyde, but you sure aren't going to be able to like trap it there for very long. So, okay, so this is kind of cool and useful if we're trying to make a carboxylic acid. That's going to give us access to a lot of the chemistry from the next couple chapters that we're going to get into, carboxylic acid derivatives. But there is actually one really cool side reaction that's sort of like this that is actually historically used as a test for do you actually have aldehydes in your molecule. So this is the Tollens test. So there's actually a ton of these old school sort of quantitative tests for like different functional groups, like you react your molecule with this thing, and if it changes colors, then it's got this functional group in it, and so forth. But This one is kind of getting covered now because it's an aldehyde reaction that is actually pretty similar to stuff that we can use for synthesis. Turns out if you take an aldehyde, you can actually oxidize it with this silver compound. I think that's a typo in the notes. I think that should be not nitrate. I'm going to leave that vague for now, I guess. Okay. So you expose it to this silver compound. You may want to double check in the book. I may have to fix the notes, but it does the same thing and oxidizes the aldehyde to the carboxylic acid. But in the process, it also reduces the silver down. Oh, sorry. I think that should actually be NO3 because, all right. All right. It is reducing the silver down though. So in the process you actually get silver 0 out of it, so silver metal. And you can tell because it doesn't actually stay in solution, it actually plates out onto the walls of the glassware that you're using. So you're holding a test tube, you have your compound in it, you add a little bit of the silver reagent, and then you stir it a bit, and suddenly the test tube looks like it's mirrored on the inside as the silver all coats out onto the inside of the test tube. So it's kind of a really cool way to check, like, do I actually have an aldehyde in the molecule? And also, I think this is actually chemistry that was once used to make mirrors, like make a really thin silver plating on one side of a glass sheet because it makes it kind of uniform even though it's really thin and it doesn't use up that much of silver, which is obviously pretty expensive. Okay, so this one you wouldn't really use for synthesis because it's not, you know, the cheapest way to do an oxidation or anything, but it is still kind of a cool one to know about historically. Okay, so questions about that? Yeah. If you have a lot of money, yes. If you start burning through silver, your advisor might have a thing or two to say about that. So yeah, really you would probably use Jones or I guess like one of the fancier versions of Jones that's a little bit like more environmentally friendly that we don't really get into because it's kind of newer chemistry. Yeah. Okay, so yeah.
On the exam, would you state the question mark?
No, so that's something you should check the book, and I'm going to have to like fix that typo in my notes because I have like silver ammonium written on the arrow and I have silver nitrate written in the text and I don't remember which one it is. Uh-huh. Is it? Okay, okay, good. Okay. Okay, thanks for looking it up. All right, so, all right, this arrow in the notes is correct and I just wrote it wrong in the text. Okay, and then, okay, thanks. Okay. Mm-hmm. Hi.
Can I ask a really quick question? So when I was doing the sampling, it said that geminal diols, like you can't isolate them, they only exist as intermediates? Is that like...
Sort of. It kind of depends on exactly what the rest of the molecule